Welcome everyone. Welcome everyone. Our guest speaker is Professor Saurya Das. The title of his talk is Quantum Raychaudhuri Equation, Implications for Spacetime Singularities, and the Quantum Origin of Lambda. Saurya, please begin your talk. You have 45 plus 15 minutes.
Okay, thank you. Thank you, Vladimir. Thank you very much. And I'll make it full screen. And when I, there you go. And when I make it full screen, I may or may not be able to see the icon. So if I can see you, if you have a question, I'm happy to answer in the middle of the talk or whenever you want. So, I'll begin. So,
okay.
Right, it's the slide is changing on its own. I'm not sure why, but we'll see. So there you go. So I hope it doesn't keep changing. If it does, oh, it is. So maybe I should move back from the. So it's changing on its own. I'm not sure why. So let me see. Is it more or less okay?
Yes, it's okay.
Okay, it's like almost full screen, but not completely.
It's okay.
Okay, thank you. Right. So I will give a, so this is a rough plan of the talk. I'll talk very briefly about quantum field theories, how, singularities are normally cured in quantum field theories, and how that procedure does not generally work for gravity. I'll talk a little bit about the Raychaudhuri equation and singularity theorems and the problem with the conclusion there, or the issues that arise, and then talk a little bit about the quantum version of the quantum corrected Raychaudhuri equation and why there are no singularity theorems in that case. And I'll then, as part of the application, I'll talk a little bit about, the quantum Friedmann equation and whether it can give something new, and then propose, as a form of the proposal, state how this suggests that a origin of both dark matter and dark energy can be a Bose-Einstein condensate, and we'll see what properties it might be able to produce. And I will summarize. This is a small picture of our university in Western Canada. You can see the Rocky Mountains in the background on a clear day. So, so singularities in electrodynamics, for example, when we have, for example, the Coulomb singularity, which is 1 over r, we know that it's resolved by quantum electrodynamics. So the Feynman diagrams, it's a renormalizable theory and everything is finite. The problem with gravity is that although it may seem that the singularity is similar as in electrodynamics, we know that the Feynman diagrams don't add up. They don't add up to finite quantities because it's a non-renormalizable theory. So therefore, this way of singularity resolution in gravity does not work, right? However, gravity is an interesting thing as well, which is singularities in space-time are places where space-time pathologies, it signals the breakdown of all physics and signals the start or the end of time, right? So that's what we normally regard as a gravitational singularity. We often take as the criteria for singularity as curvature blowing up, going to infinity. So curvature scalars going to infinity is certainly indicative, but it's neither a necessary nor a sufficient condition for the singularity or space-times being singular. For example, one can find counterexamples like infinite curvature. There is an infinite curvature somewhere, but it takes an infinite proper time to reach that singularity. So we would not really call it a singular space-time. And there are like other examples like as well. So therefore, one has come up, as we know, with a slightly different definition of singularities in gravity, which is that of geodesic incompleteness. So generally, trajectories, for example, on the one on the left, they have no beginning or no end. However, for gravity, one can show that for most reasonable classical spacetimes, the geodesics would either begin or end or both. And that is taken as a unambiguous signal for singularities. So this is where the Raychaudhuri equation comes in. And let me give a lightning introduction or derivation of the equation. We have a congruence or a pencil of geodesics, so nearby geodesics clustered together. And we define UA as the velocity field, take the total derivative, write it in terms of covariant derivatives here, interchange or exchange, switch the order. And when we do that, a curvature term gets picked up. Then we do some, like, write this as a total derivative minus, what's left over and things like that. The first term is the geodesic equation. So it's normally 0 for geodesics, right? And this quantity here can be replaced in terms of stress energy tensors using the Einstein or some similar equation. So we have this geometrical identity, so to speak. If we break it up, this quantity UA semicolon B, this is a second rank tensor. If we break it up into a symmetric, antisymmetric, and a trace part, if we decompose it this way, and we take a trace of this equation, we get this Raychaudhuri equation where one sees that this theta, which is the expansion, it is the trace of this quantity here, it signifies how quickly the geodesics converge or diverge. So for converging, it's negative, and diverging is positive. The important point or interesting point is on the right-hand side, all the terms except this one term here, in generically, the right-hand side is a negative or negative definite quantity. Therefore, if any of the pencil of geodesics or congruences were initially converging, then you can integrate this equation and one can show that the geodesics converge in a focus or a caustic in finite proper time. And you can do the calculation backwards. And the upshot is that the geodesics end and begin at this so-called conjugate point. So they focus on at 2 points, any congruence of geodesics. Now, conjugate points are therefore predicted for any congruence of geodesics due to Raychaudhuri equations. And having a pair of conjugate point means that the geodesics are no longer maximal length curve. So this picture here is an analogy for the surface of the Earth, for example. If you have a point A and a point B, then you have two great circles, right? Two geodesics. One is the shorter one and one is the longer one. See, the longer one has the two conjugate points, the North Pole and the South Pole, where the shorter one doesn't. For a pseudo-Riemannian manifold, it's the other way around. If a set of geodesics has conjugate points, as the Raychaudhuri equation shows, then that implies that the geodesics are no longer maximal length curves, right? However, maximal length curves are predicted by global arguments, on the other hand. Therefore, like geodesics, like they're not, I mean, they are on the one hand, they should be maximal length curves, yet they're not. So the only way out of this conundrum is the inference that sufficiently long geodesics cannot exist and that they're incomplete. And this is exactly what singularity, this is exactly the essence of the singularity theorems. I've simplified things a bit, but this is essentially the line of argument that follows. And since I mean, the only thing that we assume is basically the Raychaudhuri equation and the right-hand side being negative, and the right-hand side is negative for any reasonable energy condition. So therefore, this theorem holds for most spacetimes. So most physical spacetimes are singular. And it was derived, the Raychaudhuri equation was derived around the same time by Raychaudhuri, and also Landau and Lifshitz. And, Raychaudhuri was published in Physical Review, and Landau Lifshitz, the derivation is there in their book. In any case, one of the points of interesting things about the Raychaudhuri equation, or few of the points, is first is its generality. As I mentioned, it shows that all reasonable spacetimes are singular where physics breaks down. And the underlying reason why behind the generality is because essentially gravity is universal and gravity is attractive. So it's universal, so it holds good for all space-time, and attractive, therefore the right-hand side is negative. Essentially, that's the reason. The second point is that it depends on the derivation, depends closely on the fluid picture, where we have this fluid velocity field, which basically defines any geodesic or set of geodesics. So that's the second point. But the other point which remains is that the results are really, I mean, it's extremely interesting and important for spacetimes, but the fact remains that they're classical. So the result is classical. So a natural question arises as to what would happen, or how can it be made quantum, or how it can incorporate the quantum mechanics in it. So there are various possibilities. For example, one can look at expectation values of operators or Ehrenfest type theorems, which might be applicable here. But in either case, first, one of the tasks, or one of the ways, or one of the routes which one might proceed is that we have this classical velocity field u, can one replace by a quantum velocity field? Interestingly enough, such a procedure already existed, which is will be given shortly. But first, before that, to demonstrate the point, I simplify the Raychaudhuri equation a little bit, then I'll make my point, and then I'll generalize it to the most general scenario. So the Raychaudhuri equation can be written like this here, where theta is the expansion. The left-hand side tells us how fast or slow the expansion goes with proper time for any geodesic. And the right-hand side, as I said, it's all negative except this one term here. So it's mostly negative, it's generically negative. And to derive the equation, one term was ignored, which is this term here on the right-hand side. It was ignored because this is indeed zero for geodesics. This is in fact the definition of geodesics, so therefore it is zero. And for simplicity first, we write the, again, quote unquote, non-relativistic version of Raychaudhuri equation, where we replace this RCD UC UD term by essentially the Poisson equation, right? When we do that, why am I doing this? Just for simplicity, and then I will get back to the full Raychaudhuri equation. Anyway, so tau goes to t, and here in this case, what we ignore in the non-relativistic version of the Raychaudhuri equation is the non-relativistic version of the geodesic equation, which is Newton's law, right? So this is Newton's law, and this term was there, and we set it to zero because they are geodesics, or they follow Newton's trajectories. But how does this change on quantization? So if we can determine how this changes in quantization, we can figure out, or try to figure out, how the Raychaudhuri equation changes. So there already exists such a formalism. So I will quickly go through it. So right. So on the left-hand side, of course, we have classical, and the right-hand side we have quantum. I assume I start with the Schrödinger equation, and this is the reason why I chose the non-relativistic version of the Raychaudhuri equation, but it can and will be generalized, but to the most general case. In any case, if I write the Schrödinger equation, which is here, then I write the wave function, the field, as a real part and a phase. So R and S are real functions, so real fields. And I write the wave function this way. I put it back in the Schrödinger equation. I do two things then, after I plug this thing in the Schrödinger equation. First, I define the velocity field to be of the form h bar over m gradient of the phase. And this is what is done, for example, the Hamilton-Jacobi theory. And this is essentially the way of defining the quantum velocity field, which will replace the classical velocity field. And then the second thing that one does is that after the substitution, extracts the real and the imaginary part of the Schrödinger equation. One of those parts simply gives rise to probability conservation, which is great. The other part, interesting, with this definition, the other part of the Schrödinger equation is nothing but Newton's law with an additional potential, which we call V suffix q, which is the quantum potential. So the particle sees a sum of the background classical potential plus the wave function dependent quantum potential, not them individually. And the quantum potential, interestingly, it is wave function dependent, but it depends only on the amplitude of the wave function, not on the phase. So as one can see here, this is independent of S, but depends on R, the amplitude of the wave function. So now for any particle in any potential fields, force field, if it is quantum, it faces or it experiences not just the background classical potential, but the sum of the classical and quantum potential. And how does it work? Well, initially, the particles can be distributed as per, like, can be assumed to be distributed as the density, which goes as psi squared, the usual interpretation of quantum mechanics. The probability conservation equation ensures that they remain distributed like this for forever. And now each particle can be thought to follow individual trajectories subject to the sum of the two potentials, which are known as the quantal or the Bohmian trajectories, and then make a measurement in the end, right? And so if you make a measurement in between, of course, the wave function collapses, but if like don't bother until the end, then in the end, the result of the measurement of the prediction is the same as predicted by normal quantum mechanics. So this is just another way of looking at quantum mechanics. For example, so this picture, it gives all the correct quantum predictions. There's only one dynamical input, which is the Schrödinger equation. And the classical limit is easy to extract here. Just take h bar going to 0 essentially. So for example, this is the double slit experiment where each particle trajectory is subjected to the background classical potential, which is 0. It's free particles, plus the quantum potential. And if one actually numerically evolves these trajectories, these quantum trajectories, one does get back the fringes as predicted by regular quantum mechanics. If one, if there's a tuning that can be done with h bar going to 0, then the fringes go away right then, and you get like a few, two bright spots or something like that. So it's a valid picture. So more than that, so it was one of the first people who predicted that was did this formalism was de Broglie and Bohm. So now coming back to the Raychaudhuri equation, we had the Raychaudhuri equation, the right hand side here, when this is the term we set to 0 because of Newton's law. But now this term is no longer 0. This is equal to, for a quantum particle, this is equal to the quantum potential or the gradient of the quantum potential. So we put it back in, and this equation here is the quantum version of the Raychaudhuri equation, where this red term is a quantum correction term. It is wave function dependent. And interestingly enough, like it's actually, there's something more to it. But even here, for example, and it's easy to calculate that for reasonable wave functions, for example, if you have like 2 electrons or something like that with wave functions separated like by 2 Gaussians and that kind of thing, it can be shown that this term is indeed for most cases, or the cases that I checked or whatever, this term turned out to be positive. Now that's promising, because keep in mind that, for example, from any proposal for quantum gravity or any attempt at partial or total resolution of quantum gravity singularities, one has to reckon with the Raychaudhuri equation and the fact that when singularities can be resolved, there must be sufficient number of positive terms on the right-hand side to compensate for all these negative terms here, right? So that the geodesics no longer converge into, conjugate point and singularity. So it's promising that the right-hand side is like this extra term seems to be positive, right? But one can do better than that, and I will explain in a moment. But first, I would not go into the details, but this slide is, and I'm happy to answer questions later on or privately or whatever, more detailed questions if anyone has any. But so I'll not go into the details, but this is just to kind of show that I did like the Newtonian or non-relativistic version of Raychaudhuri equation just to demonstrate the procedure, but it can be done instead. We don't have to start with the Schrödinger equation. We can start with the Klein-Gordon equation, do everything relativistically. And what we have is very similar. So this is the complete, complete relativistic covariant version of the Raychaudhuri equation. And again, the comment holds that this extra term for all the wave function that we can possibly think of as reasonable, it turns out to be positive. That's a very promising sign, but it actually does better than that, because if we look at this equation, the quantal trajectories, by virtue of this definition here, right, which we defined as essentially the gradient of the phase up to some factors here. So the quantal trajectories, unlike Newtonian trajectories, they are governed by a first order equation as opposed to a second order. Therefore, the integral curves are now integral curves of this first order equation, which obviously, as long as V is well defined, they don't meet or cross, right? Because the integral curves will not cross so long as V is well defined. So therefore, for the quantal trajectories, unlike classical geodesics, there is no focusing, there are no conjugate points, and the geodesics, well, I should have, strictly speaking, I should have written here the quantal trajectories. The quantal trajectories go on forever. So there are no singularities in the sense that the singularity theorem does not appear to these quantal trajectories because, well, everything is quantum, fundamentally quantum in the universe. And the singularity theorem, like there is no singularity theorem for this quantum trajectories because there is no conjugate points for this property that I stated here. So it's an interesting consequence, I would say. So with that, let's go on to let's switch gears a little bit, and let's go on to see what if anything useful it can say for cosmology. So we as usual we assume a Friedmann Lemaitre Robertson Walker universe with A as the scale factor, and we assume A equals 1 now. And it's straightforward to go from Raychaudhuri to Friedmann equation. In fact, I put a picture here. Raychaudhuri's book on cosmology actually had one of the first derivations of this. How going from Raychaudhuri to Friedmann. So in any case, what one does is one identifies or replaces the expansion theta in Raychaudhuri equation by the log derivative of the scale factor, and as usual replaces this quantity by rho plus 3p, where one assumes a perfect fluid and stuff, and one immediately ends up with this Friedmann equation. So that's so one can go directly from the Raychaudhuri equation to the Friedmann equation. Therefore, one should, following the same procedure, be able to go from the quantum version or the quantum corrected Raychaudhuri equation to a quantum corrected Friedmann equation. So that's what we try to do here. So again, we write the Friedmann equation here, we make the identification. And now when we have the quantum corrected Raychaudhuri equation, we end up with a quantum corrected Friedmann equation, which looks like this, right? So there are a few points to be made. Firstly, the quantum corrected Friedmann equation, because it is essentially derived from the quantum potential. The quantum potential was, if one remembers, it was this, non-relativistically, it was nabla square R over R, relativistically it's box R over R, and a bunch of indexes here and there. And before I, go into the details of this, one thing which one can see is that in this case, the quantal trajectories, the comment about they're not meeting or crossing holds good here too. So for example, this picture would prevent, strictly speaking, with some caveats, but strictly speaking, if to the extent that we can trust this picture, this would prevent these trajectories from meeting, say, or intersecting into a Big Bang or something similar. In any case, let's come back to this extra term here. So this is a positive term here, as one can see, and I just suggestively write it as lambda q. Of course, the reason being that whenever one has an extra term in the right-hand side of the Friedmann equation, one naturally asks the question that could that be a source of the observed cosmological constant? So
Excuse me, may I ask a question, please?
Yes, of course.
Why is it obvious that this term is positive?
Yeah, right. So yeah, so for the particle wave functions that we tested, for example, they being represented by Gaussians or something similar, it just turned out to be positive. So it's a wave function dependent thing. So I'm not giving a kind of a theorem here that it's positive. I just the wave functions, reasonable ones that we tested, it all turns out to be positive. And from what I go from here, I will motivate a wave function from physical grounds. And then we will see that for that particular wave function, it will indeed turn out to be positive. So that's the only statement.
Okay, thank you.
Yeah, thank you. Thank you for asking. So that gives me an opportunity to qualify to clarify. So thanks. So in any case, we have an extra term, a wave function dependent term. So it depends on, what the wave function of the perfect fluid is let's just say, the background perfect fluid. So we just suggestively again write it as lambda over 3. Sorry, it's not my doing. Something's like, anyway, so it's wave function dependent. And then, right, so sorry, the hope of course is that to see if this can be a source of the cosmological constant. So this is just to remind everyone, which probably everyone knows here or experts, but for example, if one plots, the famous diagram, right, the luminosity distance, or basically the distance from standard candles such as supernovae, as a function of the redshift, it's not a straight line beyond a certain z. It turns around, and the luminosity distance, I mean, the effective distance that one sees, of course, depends on what matter is being intervened between the observer and the supernova out there. So of course, it will depend on that. And as we know that the best fit for this is proven beyond reasonable doubt within the paradigm of Einstein gravity and all that kind of thing, Friedmann FRW universe, is that we have visible matter constitutes only about 5%. We have about 70% dark energy and about 25% dark matter and 70% dark energy. We know that, right? So some of the questions which one might want to ask is what constitutes dark matter, what constitutes dark energy, or a cosmological constant, depends on how one looks at it. Why is lambda positive, right? And why is lambda so tiny, about 10 power minus 123 or 124 in Planck units, whereas from this simple-minded calculation of adding up all the zeroth mode of the harmonic oscillator modes that, let's say, any scalar or whatever basic quantum field constitutes the universe, depending on what the ultraviolet cutoff we put, the observed cosmological constant differs from the predicted value by some ridiculous amount, right? 10 power, well, 50 or 10 power 100. So it's ridiculous, right? So therefore, the question remains as to why the cosmological constant is so small. There's also another question which remains, which is that sometimes referred to as the coincidence problem, which is that the densities of dark matter in units of the critical density, let's say. So the densities of dark matter and dark energy are almost the same in the current epoch, and they're all three of the same order of magnitude as the critical density. Whereas, of course, dark matter and dark energy evolve differently. One dilutes and the other doesn't. Yet at the current epoch, it seems that they're up to the same order of magnitude. So that's kind of it's an interesting question. So what one can propose, and what we have proposed, is the following: is that we propose that for dark matter, we propose that the perfect fluid behaves exactly like a macroscopic Bose-Einstein condensate stretching across cosmological length scale. We were, of course, not the first to propose this. There are many authors before us who proposed this or very similar things. Yet we propose something something I would say new and an extension of what was there. So we also proposed this Bose-Einstein condensate idea, because the reasons being that we know that dark matter is cold, we know that it's dark, and if the bosons if the particles constituting dark matter are light, then it may avoid small-scale structure formation. And dark matter is, of course, it stretches across cosmological length scales. So if we want to have all these properties for quantum properties for dark matter, then if we assume that it's a quantum object with a well-defined quantum macroscopic wave function, then it must be a macroscopic quantum state, and there aren't too many macroscopic quantum states stretching across large length scales. Bose-Einstein condensate is potentially one of them. And as I said, many authors before us proposed Bose-Einstein, dark matter, as a Bose-Einstein condensate. However, to the best of our knowledge, we didn't, so we were probably one of the first to also kind of realize and present that while the density of the Bose-Einstein condensate can account for part or whole of dark matter, since it's a macroscopic quantum state, it comes with a macroscopic wave function. Since it has a wave function, it has a quantum potential. That quantum potential contributes to the Friedmann equation. Therefore, the quantum potential may potentially also account for some or part of the observed cosmological constant. So that was, and if it's a macroscopic quantum state, like one cannot avoid the other. They come hand in hand. And one of the strengths we think is that it has very few assumptions and very few free parameters. So the question, oh, sorry, I was going the wrong way. Yeah, there you go. So before one can pursue this idea that that we have a Bose-Einstein condensate of the perfect fluid in the background, which constitutes dark matter, and if it's a Bose-Einstein condensate, then it will contribute to the quantum potential and perhaps to dark energy. We first calculate as the question that is the critical temperature high enough, because we know that bosons will form a Bose-Einstein condensate only if it's below the critical temperature. So we calculated the critical temperature. Again, I don't remember right now whether we were the first or it was there. Some of it was there, and I think some of it we did in FRW background. I mean, in flat background, of course, this is standard calculation. I'm saying about cosmological background. In any case, so we calculated basically the critical temperature Tc as a function of the scale factor for a given Bose-Einstein condensate density. So long story short, one can do the calculation, but one can see that the critical temperature, just like the CMBR temperature, it goes as 1 over n, but 1 over a, I'm sorry, but it also depends on m power 1 over m power 1/3, where m is the mass of those bosons in electron volts. So the numbers have been all put in. So from here, one can see that as long as the mass of the constituent bosonic particles, which constitute the so-called BEC, so long as the mass is less than a few electron volts, the Bose-Einstein condensate will form, right? And in which case, so 6 electron volts, or whatever, few electron volts, a Bose-Einstein condensate would form in the early universe, and in which case the BEC density may be identifiable with the dark matter density. Now, what's more, if we assume that this quantity capital psi is the quantum potential of the Bose-Einstein condensate, and I will try to justify it in a second, but just to give kind of a, I mean, and again, this is not how we historically did it, but this is the final result anyway. So if we assume that the wave function is, for example, it's a Gaussian wave function with a prefactor which is 1 over 3 halves, a power 3 halves. This takes care of the fact that the dark matter density decays as 1 over a cube, because the dark matter density is absolute value of psi square, as it usually is. As we can see here, this also conserves the number of dark matter particles in the universe. And if we put in this wave function inside the quantum potential which enters the Friedmann quantum corrected version of Friedmann equation, we do get the quantity here as a constant. Lambda is a positive constant. So the fact that we called it lambda was just because, I mean, we were hoping that it will turn out to be some form of lambda. For this wave function, it indeed does. It indeed does give a positive constant. Now, how do we justify such a wave function? There are various ways to justify such a wave function. One simple way, for example, we go to the Newtonian limit, because why? Well, we know that from observations that the curvature of space is exactly 0 for the universe, and the curvature of space-time is also very small. It's really this small. So the Newtonian limit is a good starting point, and of course one can make corrections to it. So in the Newtonian limit, if we assume that, like, we cut out a co-moving sphere of radius r with having a density rho, which the rho is the critical density or some multiple of the critical density, right? So epsilon times the critical density, which is the dark matter density. And we know that if we simply use Newton's law of gravity, then we get back Friedmann equation. And as long as we don't look at, like, very large stretches of time or a large range of redshift, this is approximately equal to, well, sorry, this is approximately this approximately represents a Bose-Einstein condensate in a harmonic trap. And if we do that for this omega square is proportional to critical density, then again, the details can be worked out. And if there's any question, I'll be happy to answer. But if we consider this as a BEC in a harmonic trap, and then if we quantize the wave function, or we write the, well, we derive the wave function, it indeed is a Gaussian with these parameters here. So the stretch of the Gaussian, since there's only pretty much there's one parameter here, the critical density, and epsilon is whatever we want it to be, right? The dark matter density. So I just put 0.25 there. So the stretch of the Gaussian is determined from here, the width of the Gaussian. And if the width of the Gaussian is determined, pretty much the lambda q which follows is determined from here. Now, again, the next slide, in the interest of time, or I will not go into the details of the derivation, but the slide exists. And this is again just to show to derive pretty much the length, the domain of validity of the approximation under which the wave function can be reasonably considered to be a Gaussian. So essentially, this is the calculation. I'm sorry about the anyway. So long story short, one can do a systematic study to see this, to derive the limits of our approximation. And in brief, one can say that the approximation is valid so long we don't go too far in the past. So our derivations would be valid so long as I said, like one doesn't go too far in the redshift or too far in the past. But with that assumption, if we put in this wave function, I hope I have it here. It's this thing here, the wave function. So this is the wave function of the Bose-Einstein condensate. And for this wave function, the lambda q, which again, we suggestively put it as lambda, but it indeed turns out to be a constant. And if we take the rate, well, from here, one can compute rho lambda, the corresponding density, which is lambda over pi g. And it indeed turns out to be proportional to critical density. So the density of lambda, which is quantum, because it's proportional to the quantum potential, divided by the starting density. So this is just the density of the Bose-Einstein condensate, is of the order of 1. It's not 3 as we would normally require, but it's close. So we do get a constant value of the quantum potential for the wave function that we consider. So it is potentially a source of the cosmological constant. So let me kind of summarize and ask a few questions and try to answer a few, and may not be able to answer a few others. So the questions that we asked here when we apply the quantum version of the Raychaudhuri equation, the Friedmann equations, the issues we ask is in the context of cosmology, what constitutes dark matter and dark energy, or lambda? What could be a possible explanation for the smallness of lambda, which is known as the coincidence problem? In addition, of course, that lambda is positive. The ingredients that we put in once we have arrived at the Friedmann equation, the only ingredient that we put in is the assumption that we have an abundance of light bosons of light mass, less than an electron volt to whatever small mass we would like. That's pretty much the only ingredient. And this ingredient determined that the critical density of such an object is always higher than the critical temperature. The critical temperature of this object is always higher than the temperature or the ambient temperature of the universe. Therefore, very likely, if you have this abundance of light bosons, a Bose-Einstein condensate would form. And that's the implication. So BEC is created in the early universe with a quantum wave function, therefore with the quantum potential. And in this particular picture, if you ask the question, what constitutes dark matter? The answer is that it may be constituted by a BEC of light bosons. What constitutes dark energy? Well, the quantum potential of the same light bosons. Why is lambda greater than 0? Because essentially the quantum potential, it can be shown in almost all generality, I believe, that the quantum potential is opposite in sign to the starting classical potential. So quantum potential is a reaction to the classical potential, because you have a classical potential of the wave function which gives rise to the quantum potential. And And almost in all generality, if the classical potential is negative, the quantum potential is positive, and vice versa. So we start with the classical potential, which is gravity, which is attractive. Therefore, it automatically gives rise to a quantum potential, which is positive. Why is lambda tiny? Because because one showed that, because essentially in this whole problem, there's one scale, which is rho critical, and then the mathematics one can do. And again, why are they approximately equal? Again, because it is due to a general property of quantum potentials that if, for example, one is taking a stationary state of the Schrödinger or whatever equation, then the quantum potential exactly equals to the classical potential in magnitude and opposite in direction. So if one is away from stationary states, then the result doesn't hold good exactly, but it still holds good approximately, so long as one is not too far away from stationary state. So generically, quantum potentials have very similar magnitudes as classical potential. And that can be proven. You don't need to, one doesn't need to go into any specific wave function. So there's it's a provable, easily provable results. So predictions and future work. Well, we say that if there are an abundance of light bosons, then one would have the Bose-Einstein condensate and the rest. But we of course we have not identified what these bosons are, because we can't, and for now, as of now or yet. And speculations could be that they could be axions, or they could be gravitons, or they could be a new bosonic particle. We don't know, but we are studying general properties at this point. Of course, we have started the work with my good collaborators on doing a matching with all kind of available cosmological data, the ones that are coming and things like that. So it's start of a program, and we're working on it. And one of the predictions is that, again, that this model says that the lambda should have changed in the past and will likely change in the future. So that's, if one likes, that's a prediction of this model. And there are lots of corrections one can think about. For example, we have assumed that the wave function is a ground state or the stationary state. One can add excited states, and we did do a little bit more than a back of the envelope calculation, and but it's a quick short calculation. We showed that actually, if you take excited states, if one takes excited states into consideration, I'll just show one thing here quickly, which is this ratio, like from 2, it actually increases from 2. So that's a good sign, right? Because ideally we need 3. So this may not account for everything. However, if we take excited states into account, which is likely the case, the movement seems to be in the right direction. So that's all I can say. So yeah, I'm 45 minutes and I'm sort of done. So thanks everyone for your very kind attention and patience and your presence. I deeply appreciate it. And if there's any questions, I'll be very pleased to try my best to answer to them. So thank you.
Okay. So thank you very much for your very interesting talk. And now we've got time for questions. Yeah, please. Go ahead.
May I ask? Yeah. So I will make myself visible so that you don't have to speak to a ghost. I would be interested, what do you know about the evolution of uncertainties of your quantum states, and how would you interpret them?
Yeah, thank you. Thank you for your question. So the quantum mechanics that we are doing here is standard quantum mechanics. So so anything, the inferences related to uncertainties or some variations or modifications of the uncertainties would hold good. I have not done an analysis with, let's say, of the modified uncertainties and that kind of stuff with this, but it can be done. It can be done if it's deemed useful. I have not done it myself, but the standard. So if unless one changes quantum mechanics, the standard theorems and everything will hold good. But one might have a good motivation for changing the quantum mechanics itself. We can rerun this program. So, like for example, first I did it for just the Schrödinger equation, just for simplicity. Then I ran the whole thing with the Klein-Gordon equation, and one can run it for any quantum equation. So the procedure certainly exists. I don't know if that answers your question, but If you have any follow-up.
No, I'm more thinking if you have you say you can model a lambda, so this means you can model the acceleration of the scale factor. That's very fine and great. But if you also have some, if this quantum state also causes some variance of the scale factor and this increases, then one would have to interpret this, because we seemingly live in a classical universe as far as we know, and one should consider this or somehow interpret it.
Okay, yeah, I agree. I agree. That's something which would be a good thing to look at and maybe study and see what it tells us. Absolutely, yeah.
Okay, further questions, please? Comments? Remarks? So I can't hear any. So in that case, let us thank the speaker again.